Hello, this talk is about the PhD project towards next generation sea ice models, taking the rough with the smooth. My name is d.l.feltham, and I'm a professor of climate physics in the Department of Meteorology. My research interests mainly involve the polar oceans of our planet, which are covered in frozen water called sea ice. Sea ice comprises a collection of wide, thin plates of ice known as sea ice floes. The sea ice floes may be a couple of meters thick and maybe 100 to 5,000 meters wide. These floes can be distinct and separate, for example in summer, or they can freeze together to form a heterogeneous sheet of ice, which is typical of winter. I run a research group that, among other things, builds and runs models of sea ice, especially in the context of climate. This involves a fair bit of physics, maths, and computer modeling. Sea ice is a mechanical barrier to the exchanges of heat, moisture, and momentum between the air above the ice and the ocean below it. And so the presence of sea ice significantly affects the circulations of the air and the ocean in the polar regions. It also affects the circulation of the air and the ocean at lower latitudes also. Sea ice famously has a high reflectivity, reflecting a high fraction of the sun's incident radiation. Loss of sea ice results in more radiation absorbed by the ocean, and further melting of sea ice. This vicious circle is called the albedo feedback mechanism. Global warming is enhanced in the polar regions, partly by the albedo feedback mechanism. This has resulted in enhanced melting of sea ice. The Arctic sea ice cover has been reducing at a very rapid rate, and in fact, loss of Arctic sea ice is one of the most compelling indications of global warming and climate change. This project is about building physically realistic computer models of sea ice for use in climate models. The current generation of climate models were mainly built in the 1970s, though of course there have been many additions since then. These models make a number of assumptions, some of which we now know are wrong. One of the biggest assumptions was to treat the sea ice cover, which is made up of a collection of sea ice floes, as a continuous material that deforms continuously, a bit like a non-linear fluid. However, the sea ice cover is really granular, comprising a collection of sea ice floes. Treating sea ice like a non-linear fluid may be appropriate if we run our models at a coarse resolution of greater than maybe 200 kilometers in the horizontal. But the latest climate models are running at increasingly high resolutions, for example 10 kilometers, and are projected to run at much finer resolutions in the future. At such a grid resolution, the grid cell would only contain one or a few sea ice floes. Whereas the model to be representative, the grid cell should contain a statistically representative number of sea ice floes, in much the same way as you would expect a very large number of water molecules within the grid cell of an ocean model. This problem is known as continuity violation, because at such relatively small length scales, it does not make sense to treat sea ice as a continuous material, but rather as a collection of discrete flows. Almost all existing sea ice models are continuum models. This has created some doubts about the theoretical validity and, of course, the accuracy of climate models for sea ice. This project will tackle such concerns head-on. The successful student will build a discrete model of sea ice, where the individual sea ice flows are represented and their interactions modeled. This model will then be used to test the validity of the existing continuum models in a wide range of circumstances. A best-case scenario is that the existing continuum sea ice models used in climate models are largely accurate. Of course, we may not find this. Whether we find it or we don't find it, this project has potential to have a profound impact on how we think about and simulate sea ice in the future. This project is a collaboration with the Met Office and will mostly take place in my research group in the University of Reading, comprising a number of PhD students and postdocs. This project will suit someone with strong maths and physics skills and an interest in and ability to do computer modelling. These skills are much more important than any specific knowledge of climate or sea ice, which can be picked up on the project. I hope you found this description interesting and look forward to your application.